Newton's third law of motion states that for every action there's an equal and opposite reaction. This means when one object exerts a force on another, the second object responds with a force of equal magnitude, but in the opposite direction. This principle is fundamental to how our universe operates. Let's dive into gravitational force and Newton's third law. Picture the Earth and an object, say a ball. The Earth pulls the ball downward with a gravitational force, but at the same time, the ball pulls the Earth upward with an equal force. Though the Earth is massive and the ball's impact is tiny, the forces are still equal. It's like a cosmic tug-of-war. Newton's third law reveals a beautiful symmetry. In nature, forces always come in pairs. The Earth's pull on us is met with our pull on the Earth. This interaction helps maintain the universe's equilibrium. Now let's look at a few examples. Imagine a swimmer pushing off from the side of a pool. As she pushes against the wall with her feet, the wall pushes back on her. She accelerates in the opposite direction, perfectly illustrating Newton's third law. Consider a professor pacing in front of a whiteboard. She exerts a backward force on the floor. The floor pushes her forward, causing her acceleration. Again, Newton's third law in action. Finally, think about rocket propulsion. Rockets move forward by expelling gas backward at high velocity. The rocket exerts a backward force on the gas, and the gas, in turn, exerts a forward force on the rocket. This is how rockets propel themselves into space. Newton's third law and gravitational force work together to shape our world, creating balance and harmony in everything we do. Gravity is a fundamental force that shapes our universe, but how do we know it exists? Let's explore this intriguing question. First, let's go back to the 17th century with Sir Isaac Newton. Newton's law of universal gravitation states that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This law explains why objects fall to the ground and why planets orbit the sun. Newton's insights gave us a mathematical framework to understand gravity. Fast forward to 1915 and we meet Albert Einstein, who revolutionized our understanding of gravity with his general theory of relativity. Einstein proposed that gravity is not merely a force, but a curvature in space-time caused by mass. Imagine a massive object like Earth creating a dent in the fabric of space-time. Other objects, like you or the moon, move along curved paths in response to this curvature. This concept transformed our understanding of the universe. Next, consider tidal effects and ocean tides. The moon's gravitational pull causes ocean tides. As the moon orbits Earth, it creates a tidal bulge on the side facing it and another on the opposite side. These tidal effects confirm the existence of gravity. They wouldn't occur without it. On Earth, all bodies experience weight due to gravity. Weight is the downward force proportional to an object's mass. The acceleration of gravity near Earth's surface is approximately 9.8 meters per second squared, 32 feet per second squared. This consistent acceleration is a direct indicator of gravity's presence. Finally, let's look at spacecraft measurements. NASA's GRACE mission uses spacecraft to measure variations in Earth's gravity. These variations reveal differences in mass distribution beneath the surface. Stronger gravity occurs over regions with more mass underground, while weaker gravity occurs over areas with less mass. These precise measurements provide concrete evidence of gravity's influence. From Newton's laws to Einstein's theories, tidal effects to spacecraft measurements, our understanding of gravity is built on a solid foundation of evidence and exploration. Now that we understand how gravity exists, let's delve into one of the most fascinating aspects of gravity, the equivalence principle. The equivalence principle is a fundamental law of physics that reveals the deep connection between gravitational and inertial forces. Here's what you need to know. Objects of any composition fall in the same way when in free fall. Whether it's a feather or a bowling ball, they follow identical trajectories and land simultaneously. This principle has been known for centuries and was confirmed by careful experiments. Albert Einstein extended the equivalence principle by considering systems subject to both gravity and acceleration. He realized that an observer in a windowless room cannot distinguish between being on Earth's surface, under gravity, and being in a spaceship accelerating at 1g, no gravity. The laws of physics remain the same in both scenarios. Einstein's general theory of relativity unifies gravity and special relativity. It treats gravity not as a force, but as the curvature of space-time caused by mass. Objects in free fall experience acceleration due to gravity, and this acceleration is indistinguishable from acceleration in the absence of gravity. The equivalence principle is not just a theoretical concept. It has practical implications in our understanding of the universe and the functioning of modern technology. GPS systems, for instance, rely on precise calculations that take into account the effects of general relativity. So, the next time you drop a pen or feel the pull of gravity, remember that you are experiencing one of the most profound mysteries of physics, one that connects our everyday experiences to the very fabric of space-time. The equivalence principle has several practical applications across different fields of science and technology. First, let's talk about gravitational time dilation. The equivalence principle plays a crucial role in understanding this phenomenon. Clocks in stronger gravitational fields, like those near massive objects, run slower than clocks in weaker fields. This concept is not just theoretical, but highly practical. For instance, the clocks on GPS satellites experience weaker gravity compared to those on Earth's surface. Engineers must adjust these satellite clocks to account for both their relative motion and gravitational effects. Without these corrections, the accuracy of GPS navigation would suffer significantly, making everyday tasks like driving and even global logistics far less reliable. Next, consider space exploration and astronaut training. Spacecraft and astronauts experience microgravity, essentially freefall, while in orbit. The equivalence principle helps in designing spacecraft trajectories and predicting how astronauts will perceive gravity during missions. Astronauts undergo rigorous training in simulated microgravity environments such as parabolic flights and neutral buoyancy pools to prepare for the unique conditions of space travel. Gravitational wave detectors also owe their precision to the equivalence principle. Gravitational waves are ripples in space-time caused by massive cosmic events like merging black holes. These waves are detected using laser interferometers. The equivalence principle ensures that gravitational waves affect both arms of the interferometer equally, allowing for highly precise measurements. Testing general relativity is another area where the equivalence principle is crucial. Experiments involving free fall, such as the Eötvös experiment, are used to test this principle and validate general relativity. These tests not only refine our understanding of gravity, but also help detect any deviations from Einstein's predictions. In the realm of fundamental physics research, the equivalence principle guides efforts to unify gravity with other fundamental forces, such as the search for a theory of quantum gravity. It also informs investigations into dark matter and dark energy, which have significant implications for the expansion of the universe. Lastly, let's not forget gravitational redshift and satellite communication. The equivalence principle explains gravitational redshift, where light from distant objects appears shifted towards the red end of the spectrum due to their gravitational fields. Engineers must account for this effect in satellite communication systems to ensure accurate signal timing. In our journey through the intricacies of gravity, we now arrive at a particularly fascinating phenomenon: frame-dragging. Frame-dragging is a captivating effect predicted by Albert Einstein's general theory of relativity. But what exactly is frame-dragging? Imagine a massive object like a spinning star or a black hole. As this giant rotates, it doesn't just sit idly in space. Instead, it drags the very fabric of space-time around with it. Picture space-time as a vast, invisible ocean, and the spinning object as a whirlpool swirling everything around it. This mesmerizing dance is what we call frame-dragging. The concept was first brought to light in 1918 by Austrian physicists Joseph Lense and Lense-Thirring, leading it to be known as the Lense-Thirring effect. They theorized that the rotation of a massive object would distort the space-time metric, causing the orbit of a nearby test particle to precess or shift. To visualize this, think of frame-dragging as the gravitational equivalent of electromagnetic induction. Clocks in a reference frame revolving around a rotating object tick faster than those in other frames. Light traveling in the direction of rotation moves faster past the massive object than light moving against the rotation. The implications of this are profound. The Gravity Probe B experiment, which utilized gyroscopes to measure the curvature of space-time around Earth, confirmed the existence of the Lense-Thirring effect. This not only validated one of the predictions of general relativity, but also opened new doors for space exploration, gravitational wave detectors, and further tests of Einstein's theory. Frame-dragging is more than just a theoretical curiosity, it's a window into the dynamic and ever-shifting nature of our universe. By understanding it, we get closer to unraveling the deeper mysteries of space-time and gravity.